Okay, let's unpack this. Think about everything around you right now: your phone, your clothes, the power running your devices.
Hmm.
Every single one of those things and the energy that created it, it started its journey deep within the earth. Our entire modern civilization is literally built on these materials and the energy we pull from our planet.
It really is.
And here's the kicker. Our global demand is absolutely exploding. The world population has more than doubled since the 1960s, And as living standards improve, so does our appetite for resources.
It's a huge challenge.
Which brings us to some massive questions. How long can our resources sustain this pace? What environmental costs are we truly willing to accept? And can we innovate our way to viable alternatives?
Well, to even begin answering those, we first need to grasp a fundamental concept. The distinction between renewable and non-renewable resources.
Right.
Renewable resources are those that can replenish over relatively short time frames, months, years, decades. Think of plants, animals, flowing water, wind, or the sun's energy. They either regenerate naturally or are, continuously available.
So like a well-managed forest, maybe? Or just the sun showing up every day?
Exactly. Non-renewable resources, on the other hand, they formed over millions of years. On a human timescale, their supplies are essentially fixed.
Okay, that's the key difference.
Yeah. This category includes the fossil fuels, coal, oil, natural gas that powers so much of our world, and critical metals like iron, copper, uranium,
Things we dig up.
pretty much. And while we can recycle some non-renewable resources like aluminum, their original formation is just so slow that they're still fundamentally finite.
Right. Recycling helps but doesn't create new aluminum from scratch.
Precisely. It's also worth noting that some resources, like groundwater, can be a bit of a gray area. If we extract it faster than nature can replenish it, it essentially becomes non-renewable. We're basically mining it like a fixed deposit.
Interesting. So rate of use matters a lot there.
It does. And the scale of our consumption is staggering. In the U.S., each person uses roughly 11,000 kilograms. That's like 12 tons of non-metallic and metallic resources annually.
12 tons per person.
Per person, per year.
Mhm.
And our fossil fuel use exceeds even that massive amount.
Wow, that's a mind-boggling amount of material. Okay, so let's zoom in on the energy sources driving this colossal consumption. It's a striking reality that despite all our advancements, roughly 81% of U.S. energy still hinges on fossil fuels, coal, petroleum, and natural gas.
Still the vast majority.
And this fossil fuel designation isn't just a label, is it? It literally means we're burning ancient sunlight, energy stored by organisms millions of years ago, then buried and transformed over immense geological timescales.
Absolutely. These fuels quite literally built the industrial world we live in. Let's break them down. Coal, for instance, it forms from compressed plant material in ancient swampy environments.
Cold swamps, okay.
Yeah, it fueled the Industrial Revolution, provided something like 90% of U.S. energy back in 1900.
90%, huge.
Massive. While its percentage share has decreased, it still accounts for about 18% of U.S. energy today, primarily for generating electricity.
So coal is primarily for electricity now, but what are the trade-offs? I imagine mining it and burning it aren't exactly clean processes.
You're right on both counts. Mining coal comes with significant challenges. Surface mining, which now accounts for about 65% of coal extraction in the U.S., can scar landscapes, though regulations do require reclamation.
Okay, so they try to fix it afterwards?
They do. Underground mining, while less visible, has historically posed significant risks to human life and health, despite improved safety regulations now.
Right. Dangerous work.
Definitely. Then, when coal is burned, it releases several pollutants. Sulfur dioxide, which contributes to acid rain.
Acid rain. Yeah.
Nitrogen oxides leading to smog, particulate matter affecting air quality and health, and crucially, carbon dioxide, a primary greenhouse gas.
CO2, the big climate change contributor.
That's the one. And the type of coal also matters immensely. You get everything from high-carbon lignite, often burned with greater environmental impact, to cleaner, harder anthracite. This spectrum highlights a key tension. Often, the most readily available or cheapest coal is also the dirtiest, forcing a tough choice between economics and environmental health.
So it sounds like even before we burn it, the extraction itself presents enormous challenges. Okay, while coal might conjure images of massive power plants, our modern mobility and countless everyday products depend more on petroleum and natural gas. How do these compare, geologically speaking?
They're crucial. Together, oil and natural gas provided over 60% of U.S. energy in 2014. Petroleum largely dominates the transportation sector.
Yep.
Cars, trucks, planes.
Our mobility fuel.
Exactly. Natural gas is more evenly split across industrial, residential, and commercial uses. Geologically, these hydrocarbons form from the remains of marine plants and animals, accumulating in oxygen-poor ocean environments way back when.
So ancient ocean.
Ancient oceans. Over millions of years of burial, heat, and pressure transform this organic matter into liquid and gaseous hydrocarbons. These mobile fluids are then squeezed out of their mud-rich source rocks and migrate upward into more permeable reservoir rocks, like sandstone, simply because they are less dense than water.
Okay, so they move upwards, but they don't just seep out everywhere. They have to be caught somehow, like a geological net, maybe?
Exactly. That's a
Yeah.
great way to put it. They need what we call an oil trap. Think of it not as some vast underground lake, but as a specific geological structure that allows economically significant amounts of oil and gas to accumulate.
Okay.
This typically means a porous, permeable reservoir, rock like a sponge, holding the oil and gas sealed off by an impermeable cap rock, usually shale, that stops them from escaping further up.
Like a lid.
Precisely. A common example is an anticline, an upward arching fold in rock layers where oil and gas collect at the crest, sort of like air under an upside-down bowl.
I can picture that.
Geologists now use technology, like artificially generated seismic waves, to map these subsurface structures. It's vastly improved exploration efficiency.
Smart, so they can see underground.
In a way, yes. Once a trap is found and drilled into, while pressure can sometimes cause a classic gusher, pumps are typically needed to bring the oil to the surface.
Makes sense. But beyond these conventional sources, I've heard a lot about unconventional hydrocarbons, like oil sands and fracking. What are those, and why are they so controversial?
Right. These are indeed becoming increasingly important and, yes, controversial. Oil sands are basically mixtures of clay, sand, water, and a really thick, tar-like material called biomass. The oil is too viscous to simply pump out.
Like molasses, almost.
Kinda, yeah. The largest deposits are up in Alberta, Canada. Extraction often involves surface mining the material, then using hot pressurized steam to separate the bitumen. Or, for deeper deposits, they use in situ techniques, injecting steam directly underground to thin the bitumen so it can be pumped.
Sounds energy intensive.
It is. And these processes come with significant environmental concerns. Large-scale land disturbance, massive water usage, and the creation of these large toxic disposal ponds for the wastewater.
Okay, serious drawbacks. And fracking. That's the other big one in the news.
Hydraulic fracturing, or fracking, yeah. It's another unconventional method, mainly used to get natural gas out of low permeability shale deposits rock, where the gas is trapped and can't flow naturally.
So you have to force it out.
Essentially, the process involves pumping a fluid,
Mm-hmm.
mostly water, sand, and some chemicals, at extremely high pressure down a well to actually shatter the shale, creating new cracks.
Shatter the rock underground.
Exactly. The sand then props these cracks open, allowing the trapped gas to flow out. The wastewater that comes back up is then usually injected into deep disposal wells.
And the controversy.
It mainly stems from concerns about those chemicals potentially leaking into freshwater aquifers, contaminating drinking water, and also the issue of induced seismicity, small earthquakes, that seem to be linked to the deep injection of that wastewater.
Right, I've heard about that connection. Okay, so fossil fuels clearly powered our past and present, but their environmental costs are undeniable. This has pushed us to look at other powerful alternatives, some equally complex, like harnessing the atom, nuclear energy.
Mm-hmm.
It provides a significant chunk of our electricity, around 22% in the U.S.
It does. Nuclear energy is definitely, well, a double-edged sword. Its mechanism relies on nuclear fission. You bombard heavy atoms, mostly uranium-235, with neutrons, causing them to split.
Splitting atoms.
Splitting atoms. This releases immense heat and more neutrons, creating a controlled chain reaction. This heat then drives steam turbines to generate electricity, basically the same way as in a fossil fuel power plant at that stage.
Okay.
And it's crucial to understand that power plants are designed so they cannot explode like atomic bombs. The physics and engineering are completely different.
Good to know.
The fuel, uranium-235, is the specific fissionable isotope, but it makes up only about 0.7% of natural uranium, so it requires costly enrichment to increase that concentration.
Given those powerful advantages of carbon-free energy, but balanced against the very real risks of accidents and that long-term waste, what's the most compelling argument for or against expanding nuclear power globally right now?
That's the central debate, really. On the pro side, nuclear power plants don't emit carbon dioxide during operation. That offers a clear pathway for reducing greenhouse gases compared to fossil fuels. So it's a very compelling option for climate change mitigation.
The climate argument.
Absolutely. However, the cons are substantial. There's the exceptionally high cost of building and maintaining safe facilities, the risk of serious accidents like we tragically saw in Fukushima in 2011, caused by the earthquake and tsunami.
Right, a catastrophic event.
Then there's the monumental challenge of safely disposing of highly radioactive waste that remains dangerous for thousands of years. And finally, the ongoing concern about the link between nuclear energy programs and the potential for weapons proliferation.
So, huge benefits, but also huge risks and responsibilities.
Exactly. These are critical considerations for any nation looking at its energy future.
It's clear that all these big energy options come with significant challenges. So let's turn our attention now to the growing sector of renewable energy. These are the sources that regenerate and can theoretically be sustained indefinitely. In 2014, these sources made up about 10% of total U.S. energy consumption and around 13% of U.S. electricity.
Yeah, and this is where we see a really diverse array of Earth's ongoing processes being harnessed. Solar energy, for example, you can use it passively, like strategically place windows warming a home,
Simple but effective.
or actively, through roof-mounted collectors that heat water or some other fluid. For electricity generation, you have photovoltaic, PV cells, which convert sunlight directly into electricity by knocking electrons loose. And their cost has been steadily decreasing, which is key.
Solar panels everywhere now.
Getting more common, definitely. Another method uses parabolic troughs, those curved mirrors, to focus sunlight onto pipes, heating a fluid to create steam and drive turbines.
Okay. And what about wind power? I feel like I see a lot more wind turbines popping up, especially driving through flat areas.
You probably do. Wind energy converts the kinetic energy of moving air into mechanical force or electricity via large turbines. It's seen remarkable growth globally, supplying about 3% of worldwide electricity now.
3% globally, okay.
Site selection is critical, though. Profitable operations require a minimum average wind speed because the energy content increases significantly with speed. Faster wind, much more power.
Makes sense.
While it produces very little pollution compared to fossil fuels, there are challenges. Bird kills are a concern, potential land erosion around the bases, noise, and some people object to the visual impact on the landscape.
Trade-offs again.
Always trade-offs. The U.S. Department of Energy has a goal for wind to supply 20% of U.S. electricity by 2030, including expanding into offshore wind farms.
20% is ambitious. Okay, we've used water for power for centuries. Is hydroelectric still a major player?
Hydroelectric power, using falling water from dams to drive turbines, accounted for about 7% of U.S. electricity demand in 2014. So yes, still significant, primarily from large dams.
But are we building more large dams?
Not really. There are limiting factors. Dams have finite lifetimes because sediment, silt and sand, gradually fills up the reservoirs behind them.
Oh, right. They eventually fill up.
Exactly. The Aswan High Dam in Egypt, for instance, was estimated to be potentially half filled by 2025. Also, most of the best U.S. sites for large dams are already developed, limiting future expansion.
So, limited growth potential there.
For large dams, yes. Interestingly, though, there are pumped water storage systems. These act like giant batteries. You use cheap electricity during low-demand periods, like overnight, to pump water uphill to a reservoir. Then, during peak demand, when electricity is expensive, you release the water back downhill through turbines to generate power.
Clever energy storage.
It is. It helps balance the grid.
Okay. Beyond the power of sun, wind, and water, we can also tap into the heat from Earth's own core, right? How does that geothermal power work?
That's geothermal energy. It taps into natural underground reservoirs of steam and hot water. You find these where subsurface temperatures are high, usually due to recent volcanic activity or shallow magma chambers heating the groundwater.
So you need volcanic plumbing, basically.
Pretty much. It's used for direct heating. Reykjavik in Iceland is famous for it, heating almost all its homes this way. And it's used for electricity generation, which Italy actually pioneered way back in 1904.
Wow. Over a century ago.
Yeah. The U.S. is currently the leading producer, with the geysers field in California being the world's largest. For geothermal to work effectively, you need three things: a potent heat source, like a magma chamber, large porous rock layers to hold the hot water or steam, and an impermeable caprock above it to trap that heat and pressure.
Specific geological conditions needed then?
Very specific. So while it's vital where conditions are right, it's not a universally available solution.
Got it. What other renewable sources are out there helping us diversify our energy mix?
Well, we also have biomass. This is basically organic material from plants and animals. Think wood, crops, manure, even garbage.
Burning wood is biomass.
It is. It's renewable because it can be regrown or it constantly accumulates, like waste. It can be burned directly for heat or electricity, or it can be converted into methane gas, or even transportation fuels like ethanol from corn or biodiesel from plant oils.
So multiple uses.
Yes, landfills are even a source.
Mm.
The methane produced by decomposing waste can be collected and burned for energy instead of just escaping into the atmosphere.
Capturing landfill gas, okay.
And finally, there's tidal power. This harnesses the energy of moving water from tides. You typically build a dam across a bay or estuary that has a large tidal range, a big difference between high and low tide.
Huh.
The strong in- and outflow drives turbines.
Like the tides push the turbines?
Exactly. The Rance River plant in France is a notable example, the largest for a long time. However, it's geographically very limited. You really need a tidal range greater than about 8 meters or 25 feet, and narrow enclosed bays for it to be feasible. So it's not a widespread solution, but valuable in specific locations like the Bay of Fundy in Canada.
Okay, that covers the energy side of the equation, quite a mix. But as we discussed right at the top, modern society is also built on physical materials. So what does this all mean for, the things you use every day? Every manufactured product relies on minerals extracted from Earth.
Indeed. Everything.
Oh.
And it's crucial to clarify some terminology here before we dive in. Mineral resources refers to the entire endowment of useful minerals ultimately available on Earth. It's the total stock.
Everything that's out there.
Right. Reserves, however, are a much more specific subset. These are already identified deposits that can be extracted profitably at current prices and with current technology.
Profitably, that's the key word.
Absolutely. And ore is the term usually used for useful metallic minerals that can be mined at a profit. Sometimes it's applied to non-metallics, too. What's fascinating here is that a geological deposit is only technically an ore if it's profitable to mine.
So economics dictates geology in a way?
In a very practical sense, yes. It highlights the interplay between geological reality and economic factors. An element usually has to be concentrated significantly above its average crustal abundance to be valuable. Copper, for instance, needs to be concentrated about 50 times its average percentage in the crust to be worth mining. Aluminum needs about 4 times.
So it's not just about how much of a mineral is there, but how concentrated it is, and crucially, how much it costs to get it out.
Precisely. The Bingham Canyon copper mine in Utah is a perfect example of this. Mining there was actually halted back in 1985 because their outdated equipment made extraction unprofitable. The costs were too high.
So they just stopped.
They did. But then, after investing in technological advancements, like switching to huge conveyor belts and pipelines to move material, they reduced their costs by nearly 30%. Suddenly, the same rock became profitable again.
Wow, technology changed the economics.
Exactly. It demonstrates how economic factors and technology constantly redefine what qualifies as a reserve or an ore. Ultimately, all these valuable mineral resources are intimately linked to the rock cycle, igneous, sedimentary, and metamorphic processes that concentrate them. Plate tectonics provides that big picture framework for understanding how these concentrations form.
Okay, so how do these processes actually concentrate minerals into deposits we can use? Let's dive into the ways Earth actually builds these hidden treasures.
Absolutely. One major way is through igneous processes, things related to molten rock, magma. As magma cools deep within the Earth, sometimes heavy, valuable minerals like chromite or platinum can crystallize early and actually settle out due to gravity.
Like sediment in water, but in magma.
Kind of like that, yeah. Forming these highly concentrated layers at the bottom of magma chambers. We also see hydrothermal deposits. These are created by hot, ion-rich fluids, often the leftovers from late-stage magmatic processes, or groundwater that got heated by circulating near shallow magma.
Hot water dissolving minerals.
Exactly. These hot fluids can migrate along fractures in the rock. As they cool, they precipitate metallic ions, forming vein deposits. Think classic veins of gold, silver, or mercury.
Gold veins, right.
A really fascinating type of hydrothermal deposit actually forms at oceanic ridges, the mid-ocean spreading centers. Seawater seeps down into the hot, fractured oceanic crust, gets superheated, and leaches metals like copper and sulfur from the rock. This hot, metal-rich fluid then rises back to the seafloor along faults.
And what happens then?
When it hits the cold ocean water, the dissolved minerals precipitate out instantly, forming these chimney-like structures called black smokers and creating massive sulfide deposits right there on the seafloor. Ancient deposits formed this way are actually mined on land now, like on the island of Cyprus.
Wow, underwater metal factories. Even diamonds have an igneous origin, right?
They do. Diamonds form under extreme conditions at depths of around 200 kilometers under immense pressure and heat. They're then carried rapidly to the surface through these unique, pipe-shaped volcanic conduits filled with a rock called kimberlite. Most of the really productive diamond pipes are found in places like South Africa.
Incredible journeys for those gems. Okay, that's a lot of heat and pressure. What about metamorphic processes when rocks get changed?
Metamorphic processes also play a significant role, especially when existing rocks are transformed by heat, pressure, or chemically active fluids. For example, contact metamorphism happens when magma intrudes into existing rock. The heat and fluids from the magma alter the surrounding host rock, especially limestone, sometimes producing useful nonmetallic minerals like garnet or corundum, or even metallic ores like sphalerite, which is zinc ore.
So the heat from magma cooks the surrounding rock.
Essentially, yes, and
Okay.
changes its mineralogy.
Okay, those are mostly deep earth processes. But what about concentrations that form closer to the surface, where weathering and erosion are the main actors?
Good point. That brings us to surface processes, which are also crucial for concentrating minerals. One key mechanism is secondary enrichment, where weathering actually concentrates metals near the surface.
Weathering concentrates things. How?
It can happen in a couple of ways. First, weathering can remove undesirable materials, leaching them away, leaving the desirable elements enriched in the upper soil zones. The classic example is bauxite, the principal ore of aluminum. It forms in rainy, tropical climates through intense leaching that removes almost everything except aluminum oxides.
So washing away the junk leaves the good stuff behind.
Pretty much. The second way is when weathering dissolves desirable elements from the upper zones, carries them downward in solution, and then redeposits them in more concentrated forms in lower zones, often near the water table. Many copper and silver deposits are enriched this way. You often see rusty, iron-rich caps at the surface above these deposits.
A rusty signpost.
Can be. Another really important surface process involves placer deposits. These are mechanical concentrations of heavy, durable, and chemically resistant minerals sorted by currents, usually water currents.
Ah, like panning for gold in a river. That's a placer deposit.
Exactly. Gold is the classic example, leading to things like the California gold rush. But platinum, diamonds, and tin ore, often found as the mineral cassiterite, are also concentrated in placers. Water currents effectively sort these heavy minerals from lighter sand and gravel, concentrating them in river bends, potholes, or behind rock bars.
Nature's sluice box.
That's a great analogy. And following these placer deposits upstream has often led prospectors directly to the original source rock, the lode deposit, where the minerals first formed, like finding the California mother lode or the source kimberlite pipes for diamonds found in rivers.
Fascinating connection between the river discovery and the deep source. Okay, this has been an amazing journey through how Earth provides us with energy and valuable metals. But there's that whole other category of resources that often get overlooked, yet are incredibly vital. Non-metallic mineral resources. These aren't fuels, and we don't process them for their metals, but we use them for their non-metallic elements or their physical and chemical properties. And remember that statistic from earlier. These make up something like 94% of our non-fuel resource consumption by weight.
They are truly the unsung heroes of our infrastructure and daily lives, just massively important by volume. We typically divide them into two broad categories: building materials and industrial minerals.
Okay. Building materials seems straightforward.
It mostly is. For building materials, aggregate, that's crushed stone, sand, and gravel, is by far the most important in terms of quantity and value. We use nearly 2 billion tons a year in the U.S. alone. It goes into concrete, asphalt, foundations, virtually all construction.
2 billion tons, just rocks and sand.
Basically. Other examples include gypsum for plaster and wallboard, clay for tile and bricks, and limestone and shale, which are key ingredients for making cement. A key thing about these is they generally have a low intrinsic value per ton, so transportation costs are a huge factor. That means they're usually mined locally, close to where they'll be used.
Makes sense. You don't want to truck gravel across the country. And industrial minerals, how are they different?
Industrial minerals are used more for their specific chemical elements or compounds, think fertilizers or chemicals, or for particular physical properties, like hardness for abrasives, such as corundum and garnet.
So more specialized uses.
Exactly. They tend to be less abundant than bulk building materials, have more restricted geological distributions, and often require more processing, which means they can handle higher transportation costs. Prime examples are fertilizers. We rely on minerals for phosphate, often sourced from deposits rich in the mineral apatite found in places like Florida, and potassium, mainly from minerals like sylvite found in evapor deposits, ancient dried-up seas.
Literally feeding the world with rocks.
In a very real sense, yes. They're the backbone of global food security. Sulfur is another key one, essential for making sulfuric acid, which is used in fertilizer production and many other industrial processes. Its consumption is often seen as an indicator of a country's level of industrialization.
Interesting metric.
And salt, simple halite, is incredibly versatile, used heavily in the chemical industry for water softening, de-icing roads in winter, and of course as a nutrient. A great example of a mineral that bridges both categories, though, is limestone. It's used as a building material, crushed rock, cement, building stone, but also as an industrial mineral in steelmaking and for conditioning acidic soils.
Wow, limestone does a lot. Okay, we've covered so much ground today. We started by really understanding that fundamental difference between renewable and non-renewable resources. Then we took a deep dive into the complex world of fossil fuels, coal, petroleum, natural gas, and the fascinating geology of how things like oil traps form. We also looked at the environmental challenges of unconventional sources like oil sands and fracking.
The conventional and unconventional.
Then we explored nuclear energy, really weighing its carbon-free benefits against those significant risks of accidents and long-term waste. And we rounded it out by surveying the really diverse landscape of renewable power: solar, wind, hydroelectric, geothermal, biomass, and even tidal power.
Whole spectrum of options there.
And finally, we shifted gears to learn how Earth's dynamic geological processes, everything from the cooling of magma deep underground to the relentless forces of weathering at the surface, work to concentrate the metallic and those vital non-metallic minerals that are absolutely essential building blocks for our modern lives.
It really shows how intertwined our society is with these deep earth processes. And I think this deep dive into how these resources form and where they're found raises a really important question for all of us listening. As global demand for both energy and raw materials continues its steep climb, how will our deeper understanding of these intricate Earth systems guide the critical choices we need to make today? Choices about balancing resource extraction with environmental stewardship, and ultimately about securing a truly sustainable future for everyone.